Pseudorandomness and the AdS CFT correspondence. Please take it away.
All right, great. Yeah, thanks so much for your help. And for the introduction. So I'm going to be talking about pseudorandomness and AdS CFT, and this is all going to be based on joint work with Bill Fefferman and Umesh Vazirani. There we go. Okay, great. So the starting point for this talk is an interesting question, which is, can quantum circuit complexity be physical? That is, could quantum circuit complexity be a measurable or physical quantity like heat or distance or time? And at first glance, this might seem like a somewhat strange philosophical question, but this has actually been considered as a serious proposal in the AdS CFT and from qubit communities. Namely, in particular, there's a proposal of Susskind and many other collaborators that circuit complexity is actually physical in the context of AdS black holes. So let me remind you a bit of the background here of this proposal. So this proposal is made in the context of the AdS CFT correspondence, which is this conjecture duality between a quantum gravity theory in anti-de Sitter space, this theory that's living on the left, and a quantum mechanical conformal field theory that lives, say, on the right. And the basic idea with this correspondence is that there's some dictionary which maps between the Hilbert spaces of the respective theories. So it maps states in one theory to states in the other theory, and operators in one theory to operators in the other theory. So the dictionary is some sort of homomorphism between these two theories. So you can see why this is kind of a very interesting suggestion. It's kind of suggesting that maybe there's a way of constructing a theory of quantum gravity or studying it by studying the dual quantum mechanical conformal field theory, which lives on the boundary of the spacetime. Now, this dictionary is not something that has been fully worked out. I would say it's something that's still under construction. There are a lot of really nice examples of quantum states that we believe are dual to particular gravitational phenomena. But it's something that's there's very good intuition and arguments as to why this should exist. And it's kind of an active area of work to try to construct this correspondence and figure out what it means for quantum gravity theory. Now, one particular paradox or kind of challenge that's arisen when trying to formalize this AdS CFT correspondence is something that I like to call the wormhole growth paradox, which is a paradox that dates back to 2014 to a work of Susskind. And the paradox is very simple to state. The paradox is basically noting that there are certain systems in gravity such that their equilibrium properties look very different than their dual quantum mechanical system. So what do I mean by that? Well, in particular, in classical GR, we know there are some solutions to Einstein's equations, called the two-sided AdS wormholes. And these are kind of gravitational systems that really do not equilibrate quickly. So classically, there's some wormhole connecting two spacetimes, and the volume of this wormhole just grows linearly forever. At least for an exponential amount of time. Classically, it actually just grows forever. So this is a system that kind of never equilibrates. So if you were to plot, say the wormhole volume versus time, this is what the plot would look like. It just goes up forever. On the other hand, it's believed that the quantum mechanical conformal field theories, which are dual to these black holes, look very different in terms of their equilibrium properties. In particular, these are theories that very rapidly equilibrate or very rapidly thermalize. So think of them as systems that are kind of like a blender. Like whatever quantum mechanical state you throw in, it kind of rapidly gets mixed up on some particular characteristic time scale. So to make this a little bit more formal, what's believed to happen in these quantum mechanical theories is if you had some local observable O in the quantum mechanical theory, and you plotted its expectation value versus time, well, that expectation value would very rapidly equilibrate to its equilibrium value in the theory. So the graph would look more something like this. After some polynomial amount of time, it would just kind of level off. There could be some tiny oscillations around this level off, but it basically just levels off. So this gives rise to a question, if there's a kind of full duality between these two theories, what quantity in the CFT could possibly be the quantum mechanical dual to the wormhole volume? Kind of from the information I just told you, you know that the dual quantity could not be some locally defined operator, because it just wouldn't have the right equilibrium properties. So what on earth could this dual quantity be? So in the same paper in which Susskind pointed out this conundrum, he also proposed a resolution of this paradox. Namely, he proposed that the dual quantity to wormhole volume might be the circuit complexity of the quantum mechanical state. That is to say, the minimum number of, say, 2-qubit gates or local quantum operations that you need to transform some fixed reference state into the quantum mechanical state of the CFT. So this is called the complexity equals volume conjecture. As we all know, there have been a number of variants of this conjecture suggested, like complexity equals action and things like this. I'll just call all of these under one umbrella complexity equals volume, because the differences between these different flavors won't matter very much for this talk. Okay, so in other words, this proposed solution is that circuit complexity is physical. That is to say, the circuit complexity of these states actually plays a role in the physical theory because it's the dual to volume. So what was the intuition as to why this might be a reasonable dual? Well, the basic intuition was something like this. So if you look at the state of the conformal field theory after time t, well, it's given by some evolution of some initial state by some particular CFT Hamiltonian H. So it's, e to the -8 IHT applied to some initial state psi, right? And, this Hamiltonian evolution, you can think of it as you're just really applying the same unitary operator, again and again to the theory. Like if we discretize time, this is just like you just take some quantum circuit U and you just apply that circuit again and again to this initial state. And the basic intuition here is that the complexity of the state e to the -IHT psi relative to psi, that is to say the number of gates you need to transform between them, should grow roughly linearly with time, because intuitively there shouldn't be any shortcuts to preparing the state. So in other words, if the most efficient way to prepare e to the IHT psi is actually to start with psi and time evolve for time t, if there are no shortcuts there, then the complexity of the state would indeed just scale linearly with time, exactly matching the behavior that the volume should have. So that was kind of the high-level intuition for this proposal. And of course, this is a very interesting and creative proposal. So there have been a lot of works trying to create supporting evidence for the proposal, both from the kind of complexity side, trying to argue that it's reasonable that there are some Hamiltonians for which the complexity of e to the IHT psi should grow linearly with time. So there have been works of Aronson, Brandau-Bodanowicz, and Balasubramanian and all, which we saw a talk on earlier this week. And on the other hand, there's also been work on the gravity side, trying to argue that that kind of the behavior of the wormhole volume indeed has some kind of further properties that one might expect that kind of match the properties that complexity would have on the CFT side. And here I'm thinking of works of Stanford and Susskind and Stanford and Schenker, and others. I'll explain these a little more in detail later in the talk. Okay, so that was the proposed resolution of this wormhole growth paradox. But if you tell this resolution to a theoretical computer scientist, they tend to get very worried. And why is this? Well, the reason is that computational complexity theorists have been studying circuit complexity for a long time. And it turns out to be a very finicky or a very strange quantity. It's something that's very difficult to pin down. So it seems like something seems wrong here. You should be very wary when trying to attribute this physical reality. So kind of here be dragons in the theory. So why is this? Why does this suggestion make computer scientists uncomfortable? Well, it's because there seems to be some sort of type mismatch between the way that computer scientists think of complexity and the way that people think of wormhole volume. So what is this mismatch? Well, the basic mismatch is this. So we've known since classic work in the 90s that in general, circuit complexity is a quantity that's extremely difficult to feel or estimate. So if I give you, say, a black box function, and I want you to tell me, what's the circuit complexity of this function? Is it very low or very high? We've actually known since the 1990s that that's an extraordinarily difficult problem. Like it would take exponential, even more than exponential time just to answer that question. On the other hand, wormhole volume sounds like something that should be very easy to estimate. Like, I don't know, when you tell this volume to a computer scientist, it sounds like something that if you were in the theory, you would just take out some tape measure and kind of measure the length of the wormhole volume. It sounds like a very easy to measure quantity. So, there seems to be some type mismatch between, you're connecting something that's hard to measure with something that's easy to measure. But it turns out that formalizing this discomfort is actually surprisingly subtle. And that's kind of for two reasons. Well, the first reason is that really only a very special subset of quantum states are being considered in this complexity equals volume conjecture. So you might think that maybe the complexity of these states is actually easier to estimate than it is for kind of generic quantum states, like from these that are used in these complexity theoretic works. Secondly, from the gravity side, it's actually known that no single observer living in the wormhole can actually estimate the wormhole volume. The reason is that observers living in the wormhole only have some kind of finite amount of proper time before they crash into the singularity. It's actually not long enough to kind of measure the full length of the wormhole volume. So then there's this second possibility that maybe this wormhole volume is something that's somehow inaccessible in the theory. That would be another way of kind of avoiding this type mismatch. So in this work with Bill Fefferman and Umesh Vazirani, we sought to ask, can these intuitive objections to this complexity equals volume conjecture be realized? And if so, what would this mean for the AdS CFT correspondence?
Sorry,
so
just a
sure.
very naive question, but I'd say one of the advantages of duality is that a question that might be very hard to ask in some variables might be very easy in the dual description. So
yes.
Could you say a bit more why I
yeah,
feel like
sure.
saying here that this is even harder, even if there's a duality, this should not be easy.
Well, yeah, well, I'm saying so it could be that the duality actually does connect something that's hard to compute to something that's easy to compute, but then that would imply the duality itself is difficult to compute. So I'll get to exactly what this means in just maybe 2 or 3 slides, actually. But I guess, yeah, one could worry that that can make the duality too good to be true or something like that. So that's, but I have some more provocative theses and things to discuss the interpretation of this in a few slides.
Sounds good.
Okay, great. So what was our result? Well, our first result was to instantiate this complexity theoretic objection in the context of complexity equals volume conjecture. So in particular, we created a form of something called computational pseudorandomness within this very small set of quantum states that live in this dual quantum theory. And I'll explain what this means in a little more detail soon, but the basic idea is that we create some ensemble of quantum states which are really difficult to distinguish from one another, and yet were created with very different lengths of time evolution and therefore very different wormhole volumes in their dual theories. So this computational pseudorandomness construction that we make is actually very, very powerful. It actually says that what whatever quantity is the dual to wormhole volume. It could be complexity. It could be some log of a 2-point correlator. It could be kind of any quantity that has the right behavior. Whatever quantity you have in this quantum mechanical theory that grows with time, it has to be something that's very difficult to compute given the CFT. So this discomfort with having to pick something like complexity as the dual to volume is something that's actually inevitable in AdS CFT. So this is not something that's particular to picking complexity as the dual. It's actually any quantity that grows with time in the dual in this way is something that should be very difficult to feel or estimate if you're only given the CFT state. And I will describe in more detail later in the talk what is this pseudo-randomness a little more precisely and how do we actually construct it in the context of the theory. But this is the high-level picture of our pseudo-randomness results. The second thing that we showed is that the wormhole volume is indeed something that's easy to compute. So in particular, we give an efficient quantum algorithm, which given kind of a description of the AdS state, achieves a very rough approximation of the wormhole volume of that state. Okay, so now you might ask, so how does this square with my prior statement that no one observer can measure the volume? Well, I can explain that, and it basically the answer to that question depends a little bit on exactly how you think the AdS state encodes the bulk geometry. So if you believe that AdS CFT and the dictionary allows you to extract kind of the entire metric of the AdS space, then I think it's quite clear that computing the volume is then a really simple exercise, a very simple calculation. This would be like if the AdS state encoded the bulk geometry in the same way as you would simulate, GR in your classical computer. You have some discretized metric. Then you can very easily compute the volume of a wormhole interior of a metric. On the other hand, if you have a more kind of complementarity-like picture of AdS CFT, and let's say that you think the dictionary is more limited than that, like it only allows you to reconstruct the experiences of single observers living in the bulk, then actually we claim that even in this case, there still would be an efficient algorithm to estimate the wormhole volume. And the algorithm would go something like this, like suppose that you instantiate polynomially many observers in the wormhole. And these observers, they could either meet pairwise and exchange messages with one another if they happen to be close, within some certain characteristic distance in the wormhole, and otherwise they would not be, right? Like if they were kind of far apart, then they wouldn't be able to exchange messages. So the basic idea is that, well, maybe we could just put a bunch of observers in the wormhole, just roughly count how many of them were able to talk to one another before they crashed into the singularity, and then post-processing the results of all of these experiments would give one a very coarse approximation to the volume. Okay, now you might say post-processing, that sounds like something crazy, like these experiments that we're talking about are space-like separated in the actual geometry. Like, these different observers couldn't actually speak to one another if they were living in the theory. So why is it reasonable to assume you could post-process their outcome? Well, the basic idea is that if you assume something called the quantum extended Church-Turing thesis, which is this kind of thesis that all physical processes, including quantum gravity, are efficiently simulable with quantum computers, then all you would need to do is simulate the experiences of those observers on a quantum computer, and then classically post-process the outcomes. So that's kind of exactly the algorithm that we give. There's no need to actually throw the observers into this space. Simply simulate the experiences of these observers in the space, and then run some classical algorithm to count how many of them met up afterwards. And that would, again, give you a polynomial time quantum algorithm that estimates the volume from many copies of the AdS state. So this would be kind of an instantiation of the statement in complexity theory that VPP to the BQP is equal to BQP. In other words, classical post-processing doesn't change the power of quantum computation. This is kind of an instantiation of this in the context of volume. So let me just emphasize that our claim that wormhole volume is measurable, it's not coming from an experiment that's physically implementable. Rather, we're claiming that there's some sort of computational efficient algorithm that allows you to extract the volume from the state. So the information is there, and it's easily extractable, even though it might not be observable to any single person living in the space. So those are our volume results. So let me say now in a nutshell what this means for AdS CFT. Well, our first result was this pseudo-randomness result. It said that whatever this dual quantity question mark to volume is, it has to be difficult to compute, has to be something like complexity. On the other hand, the wormhole volume is easy to compute or estimate. What does this mean? Well, this means that this duality is connecting something that's hard to compute and relating it to something that's easy to compute. Well, in particular, that means that this dictionary itself must be exponentially difficult to compute. So this would be like in classical computer science, if you took an NP hard problem and you reduced it to a very easy problem, then you would either mean you'd shown P is equal to NP, or else you just really performed an exponential time computation in your reduction. That's exactly what this might mean for the AdS CFT correspondence. It might mean that this dictionary that maps the going from the CFT state to the gravity state is something that has to be exponentially difficult to compute, at least when you're trying to reconstruct wormhole interiors. Now, there's one other possible implication of this for quantum gravity. There's another way. There actually is a way to escape this conclusion that the dictionary is exponentially difficult to compute. And this would kind of say that AdS CFT has to be kind of permanently under construction. That is to say, there'll never be a very simple way of deducing everything happening in the wormhole interior. There's one other way out of this, which is that it could also be that the quantum extended Church-Turing thesis is false in quantum gravity. So in particular, if it turned out that the quantum gravity dynamics that occur on the interior of wormholes are exponentially difficult to simulate even with a quantum computer, then you would not necessarily have to conclude that the dictionary is exponentially complex. So what our result is saying is that kind of the or of these two statements is true. The dictionary has to be exponentially difficult to compute, or else quantum extended Church-Turing thesis should be false in quantum gravity, or potentially both of them. So it's not an exclusive or, it's just the or of these statements. So I'm going to discuss a little more at the end of the talk exactly how one might interpret this from a philosophical level. So I'm going to conclude with some provocative theses as suggested about what this might mean. But that's kind of the very high level picture of what our result says. So with my remaining time, I'm going to try to tell you a little more about the core part of our argument, which is establishing that it's possible to construct pseudo-randomness within the small subset of states that are considered in the CFT. Okay, so in order to describe this, let's first just define what states are allowed in the CFT in the first place. So let's model the CFT as a system of n qubits, where n is the entropy of the black hole. Now, these qubits initially begin in a particular state called the thermal field double state. And the details of the state actually aren't important for us. It's just some low energy state of the CFT Hamiltonian HCFT. And then the state evolves according to this CFT Hamiltonian. So it evolves like e to the minus IHT times the initial state. And from a computer science perspective, it's helpful to make a kind of discretized picture of this system. So we know that in the CFT, there's some kind of characteristic time t naught. That's the scrambling time. This is some characteristic time such that after this much time, this evolution by e to the IHT kind of diffuses local perturbations throughout the system. So let's define evolution by a scrambling time by the unitary u. So the states that we're considering are states that are of the form like u. You just apply u many times to this initial state. Now, if that were kind of all complexity equals volume we're talking about, it wouldn't be a very interesting theory because this is kind of a very tiny subset of states. So actually in complexity equals volume, there's actually a slightly larger family of states that are being considered here, which is that we also allow some small number of perturbations to this time evolution to be applied to the system. So in the CFT system, this is perturbation by some kind of very low energy, like thermal scale local operators. In the model with kind of qubits, we can think of this as you're allowed to perturb this evolution by inserting some small number L of single qubit gates. So each insertion by a single qubit gate, does increase the energy of the state by a small amount. And on the gravity side, we know that these local operator insertions correspond to throwing shock waves into the wormhole. So those actually, those actually perturb the wormhole geometry a bit. So the state after the insertion of L shocks looks something like this. You apply U, then you apply some local operator O1, then you apply U again, you apply some local operator O2, et cetera, et cetera. And I want to emphasize that the number of these local operator insertions that you can apply has to be much less than n. Why is this? Well, this is just because these insertions are increasing the energy of the state. So you have to limit the number of shocks you can throw in. Otherwise, it's not clear that kind of the dual state would have a simple semi-classical description with a well-defined geometry, et cetera. So you can just think of this as, it's like the normal time evolution, but you're allowed to make these small number of perturbations. And it's actually precisely this set of states for which there's been evidence provided that complexity equals volume is true. So you might be familiar by these works of Schinker and Stanford and Susskind, who showed that kind of the changes that occur to the wormhole volume induced by throwing in these shocks, matches the changes that one would expect to find to the complexity of these states under adding operator insertion. So this is sometimes called the switchback effect. At least up to some kind of leading order, the behavior of the volume matches the behavior of the complexity for these particular states. Okay, so the central question we'll be asking is, how hard is it to estimate the circuit complexity of such states? So how will we formalize this? Well, what we're really asking is, if I gave you many copies of a state of the above form, but say I didn't tell you which one of the states it was, like I didn't tell you which local operators I inserted or when, how difficult would it be for you to estimate the circuit complexity of the state, which roughly ends up being the number of times that you applied U? All right, so how does one normally do this? So the standard tool that one can use to show that it's hard to estimate circuit complexity would be to try to show that these states form a unitary T design. And if you were able to do this, this would show in an information theoretic sense that it's impossible to measure the complexity of these states. So why is that? Well, if you show that these states form some unitary T design, then that means T copies of the state are indistinguishable from T copies of a Haar random state. We know that Haar random states have maximal. Sorry, go ahead.
Go ahead.
Sure. Was my connection interrupted, or is everything good?
We still hear you. At least I still hear
Okay. Okay, great. Okay, so the basic idea is that if you showed these were a T-design and they're indistinguishable from Haar random states, we know Haar random states have maximal circuit complexity by a counting argument. These states have very low circuit complexity because we only applied some polynomial number of times. So these have polynomial circuit complexity. So that would immediately imply that the complexity of these states is hard to estimate. So that's maybe the most natural way to show this. But it turns out that this can't work. The reason is that there's a simple counting argument that says that an ensemble of states of this form can't even be a unitary one design. So that's because there's a simple counting argument that you need 4 to the n distinct states to have a one design. Like for instance, the Pauli group is a one design. But on the other hand, we only have 4 to the L possible states here because you can apply, say, one of the 4 different Pauli operators at each of the L shock points. But the number of shocks we're allowed is too small. We can't apply n shocks. We have to apply something much smaller than that. Think n to the epsilon shocks for a very small epsilon. So we won't be able to use these information theoretic tools here. So instead, we're going to use an alternative tool. And this is the notion of computational pseudorandomness. So this is a tool that's fundamentally a computer science-based tool and not one that's based on information theory. So what is quantum computational pseudorandomness? So the classical analog of this has been known for a long time, but it was recently formalized in the quantum context in a nice paper of G. Liu and Song. And what it is you call an ensemble of states psi k a quantum pseudo-random state ensemble if the following 2 properties hold. The first is that these states are all very easy to prepare. So each of them can be prepared with only a polynomial size quantum circuit. So these are all states of low complexity. But on the other hand, they're computationally indistinguishable from Haar random states. So what does that mean? It says kind of, if you only had polynomially many copies of the state and only a polynomial amount of time to look at those copies, then you wouldn't be able to distinguish them from that many copies of a Haar random state. So this is different from information theoretical indistinguishability because it's really a computational statement. So for these states actually are information theoretically distinguishable from random with a small number of copies. But it's just saying that that information is not something that's computationally accessible to you. So the information is there, but you just can't read it. So. And in their same paper, and then also in the nice follow-up paper of Bukursky and Shmueli, they actually gave an efficient construction of quantum pseudo-randomness based on kind of ideas from post-quantum cryptography. So the details of this are not important, but just kind of for your background, they showed something like if you have kind of a pseudo-random function fk of x, which is based on some post-quantum cryptography, like the learning with errors problem. If you think it's hard for quantum computers to can distinguish from random, then you can show that if you create an equal superposition state and give each element of the equal superposition a pseudo-random phase, then you can actually show that that these states are indeed computationally indistinguishable from Haar random states. So the details of this are not that important, but really what they showed here is that if you have a universal quantum computer, then there is a way of constructing quantum computational pseudo-randomness as long as you believe cryptography is still possible in the presence of quantum computers. Okay, so let's go back to our initial question then. So, again, we want to ask, are these CFT states a pseudo-random state ensemble? So these are states like you apply U, and then you perturb it with a local operator, then you apply U again, etc. If so, this tells us the complexity is difficult to estimate. But what's clear is that this is a very limited subset of states, right? It's not clear how to perform universal quantum computation with states of these form, because we're only accessing a very kind of small corner of the Hilbert space here. So unfortunately, we cannot use this prior construction of G, Leo, and Song in order to argue that our CFT states are a pseudo-random state ensemble. All right, so that means we're kind of out of luck here. So we're going to have to make our own candidate pseudo-random state ensemble construction. So that's precisely what we do in our work. So we're going to make a custom pseudo-random construction, which has a very different inspiration. In particular, we're going to take inspiration from block ciphers like the AES and DES crypto systems in order to create our quantum pseudo-random state ensemble. All right, so what's the intuition for our pseudo-randomness construction? So the intuition is very simple to state. So first of all, I just want to note that even though evolution by a scrambling time, this operator U is very scrambling, the state that you get just from applying U many times to this initial state is not something that's pseudo-random. Well, why is this? Well, this is because I'm just assuming that everyone knows the CFT Hamiltonian. So if you were given the state of this form, you could just time evolve the state backwards until you run into the thermal field double state. And that would allow you to very quickly estimate the length of the time evolution that you apply. So the basic idea, so that means we need to do something more here. And the basic idea of our construction is that we're going to apply the shocks to the state, but we're not going to reveal the pattern of shocks that were applied. And the basic idea is that by doing so, we can use these shocks to help obscure the length of time evolution that we applied to this initial state. So why does this help you obscure the length of time evolution? So, okay, so let's formalize this. So we're saying we have this fixed operator U, and let's say we have some secret key K. This secret key is just a string of L different elements of the 1-qubit polygroup. So our state psi k is then just the state obtained by applying U, then applying the first element of the key to the first qubit, then applying U again, then again applying the second element of the key, etc. And the basic idea is that these application of poly operators create some sort of branching points in the evolution. So in particular, you can use these shocks to define a tree of the different states you could have ended up in from this construction. So you know the root of the tree. So the root of the tree is the thermal field double state. Then the next layer of the tree is the 4 different states you could have ended up at after the application of a single perturbation, right? So you either applied U and then an identity, or U and an X, or U and a Y, or U and a Z, right? And then this process kind of repeats itself, right? So this defines a kind of tree of quantum states. And the size of this tree is, like 4 to the L. So, if you look at the number of states, that you could have ended up with after L shock insertions, there are 4 to the L different states here. And the basic intuition here is that, if U were kind of a very generic unitary, say if U were a Haar random unitary, then we know that, each state in this tree is nearly orthogonal to every other state in the tree, right? This is just because of the simple fact that if you take a Haar random state and then apply, say, a poly X on the first qubit, there's a simple calculation you can do to show that, the norm of the inner product squared between your state before you applied X and after you applied to X is inverse exponentially suppressed. So these states are all almost exactly orthogonal to one another in this tree. And our basic claim is that, if I gave you an unknown state psi, it would be very difficult for you to tell if it is one of these exponentially many states that lie in this tree, or if it had kind of nothing to do with this tree, if it were, say, an independently hard random state that was not constructed in this way. And what's the intuition here? Well, the intuition here is something like this. Like, suppose that you were kind of a random or very generic scrambling unitary, and all you could do was access U or U inverse as a black box. So let's say that you didn't know what pattern of operator insertions was applied. I just gave you the final state at, say it's one of these states that's at the leaf of the tree. How would you possibly tell which state you were at? Well, one thing that you could try to do is you could try to say, well, okay, I'll try time evolving backwards, and then I guess, I'll maybe guess a different Pauli operator that was applied, and then time evolve backwards again, and try to find my way back to the thermofield double state. Well, the intuition here is that that's going to be extremely difficult, because kind of if you make even a single mistake in trying to traverse this tree backwards, you would just end up with a state that's almost completely orthogonal to the state you wanted to end up with, right? So the intuition is that, so you won't be able to tell if you ended back up at the thermofield double, because if you made even a single mistake because of this chaotic evolution, you would end up with almost no overlap with the thermofield double. So we can formalize this in a computer science sense. So the main claim of our paper is that, if you only had access to the scrambling time evolution in some sort of black box access to U and U inverse, then the number of queries to that black box you would need to distinguish one of these states in this tree from a truly random state would scale exponentially in the number of shocks that you are allowed to apply. And so this is the claim that we give evidence for in our paper. So actually, the most rigorous version of our proof is for a simpler classical version of this quantum system. But I think it would be very easy to generalize this to this kind of fully quantum black box model. And what we're then conjecturing is that the security of the pseudorandomness construction still holds in what's called a white box model. That is to say, we're conjecturing that this evolution by scrambling time is sufficiently generic or scrambling that that this construction is still secure, even if you know everything about the CFT Hamiltonian. So this is not something that one would ever be able to prove, because well, first of all, it's not clear if we have an explicit description of what the CFT Hamiltonian would be in this qubit model. But secondly, it's also it's also something that would be kind of beyond the scope of quantum complexity theory, because in order to do that, you'd have to effectively prove that P is not equal to NP. Like, you'd have to prove that cryptography is possible. But I think that this gives very strong evidence that these states are indeed pseudo-random. So that's our construction. So why is this construction plausible? Well, it turns out that this construction looks really similar to what's a classical cryptography techniques called block ciphers, which are actually the heart of the AES crypto system, which is used in the way that we encrypt the internet today, in conjunction with RSA. So let me give you here's my kind of physicist, here's my explanation of the AES crypto system for physicists. So how does this crypto system work? Well, let's say you're trying to encrypt some message X with some secret key. And let's say that you have some permutation sigma of n-bit strings, which is publicly known, but it's a permutation that's very highly scrambling. So it just mixes up these strings kind of in a totally unstructured way. The way that the AES crypto system works is the way that you encrypt the string X is you take your initial string X, you apply this known permutation to it, you then XOR in the secret key to every bit of the string. So x to the k is just, you apply your secret key as a bitwise OR to every bit of the string. Then you apply sigma again. Then you apply the key again, et cetera, et cetera. So you just repeat this many times. And the basic intuition of this crypto system is that, it's very easy to invert if you know the secret key, right? You just, invert sigma, then apply the key, then invert sigma, then apply the key, right? You just run it backwards from here, right? But if you don't know the secret key, or say if you're even wrong on a single bit of the secret key, then because this permutation is so scrambling, you would just end up at a totally wrong string if you tried to decrypt it with the wrong key, right? So there would be kind of no information given to you. You would just end up with a totally random answer that had nothing to do with the string X. So that's the intuition for why classical block ciphers work. So you can now clearly see that the pseudo-random states that we're constructing look exactly like the quantum version of a block cipher, right? This scrambling unitary U is kind of the quantum analog of this highly scrambling permutation sigma that's used in symmetric key block ciphers. And instead of applying, flipping certain bits as you evolve in the classical block cipher case, instead we're now just applying local poly operators. So actually, we give a rigorous proof that this analogous kind of classical block cipher is actually black box quantum secure, and this is kind of the rigorous basis for conjecturing that these CFT states are pseudo. Okay, so let me just wrap up with what we saw for our pseudo-randomness results. So what did we do? So we showed that the states that are in the CFT, that are the states that are believed to have duals with well-defined volumes, we showed these states are plausibly pseudo-random. And why is that? Well, it's because that the scrambling nature of the CFT evolution actually makes our construction look very much like a quantum analog of a classical block cipher. So this immediately implies that estimating the length of time evolution of one of these CFT states is something that should be exponentially hard, even for quantum computers. And the reason is that once you show these states are pseudo-random, then so that means they're indistinguishable from hard random states. That immediately implies that they're also indistinguishable from one another as well, just by using the hard random state as kind of a hybrid and kind of a proof argument. There's no need to ever instantiate hard random states in the theory. So again, this means that any quantity that grows linearly with time is hard to estimate, because if you make this pseudo-randomness construction, with say n squared different applications of this scrambling evolution versus n cubed, then those should be indistinguishable from one another, but would have very different volumes and lengths of time evolution. All right, so I'm now going to conclude with a few provocative theses to kind of simulate discussion. So what does this mean for AdS CFT? So, again, our result is saying that, either the dictionary has to be exponentially hard to compute, or else the quantum extended Church-Turing thesis is false in quantum gravity. I'm going to claim that there are two kind of different philosophical ways that one could view this result in light of what it means for AdS CFT. So the first kind of approach to thinking about this, is you might say that this result, that the dictionary has high complexity, you might worry that this is kind of a bug in the theory. So why is that? Well, you might worry that the fact this dictionary has high complexity in wormhole interiors might in some ways limit what one might hope to learn about quantum gravity inside of a wormhole from the conformal field theory states that are their dual. So this could be bad news. One could see this as bad news for AdS CFT. Of course, actually, has been pointed out by many people, this was actually, I think, already expected and in the sense that I think people already realize that the interior reconstruction is something that's extremely challenging. So this could just be kind of formalizing some of the intuitive arguments that were previously given for why this is the case. But it could be that this kind of high complexity dictionary, it could be that something that's very limited in its damage, though. Like it might only affect some very narrow aspects of the theory. So in particular, in the recent paper, Lenny Susskind suggested that maybe this result is pointing towards what he calls a computational cosmic censorship conjecture, which is he conjectured that all violations of the quantum extended Church-Turing thesis, or these exponentially complex dictionaries, must be shielded behind horizons. So this would be a conjecture that, yeah, things can go wrong here, but they only go wrong on kind of the interiors of wormholes or sort of kind of very strange places in these space-times, and for the parts of the space-time that are causally connected, or that are easily accessible from the boundary, then nothing strange is happening. So he proposed this as kind of the complexity theoretic analog of Penrose's famous cosmic censorship conjecture from the 60s, that singularities in G are shielded by horizons. Now there's another way of viewing this our result, which is you might actually view the complexity of the dictionary as a feature of the theory rather than a bug. So this has been pointed out both in Hayden Harlow and also in a recent paper of Kim, Preskill, and Tang. In fact, I believe there'll be a talk on that paper tomorrow, in which they propose, their paper was talking about a one-sided black hole rather than a two-sided wormhole. But so a slightly different setting, but they had, both them and Harlow Hayden have this kind of nice idea, which is that there might be some form of computational protection of causality that's arising from this complex dictionary, which is to say that, even though, say, the interior and exterior of a black hole are dual to one another, maybe the high complexity of the map between them is what protects causality in the theory, because it prevents someone kind of sitting on the boundary at the outside of the theory to kind of instantaneously modify the interior of the wormhole or the black hole. So this could actually be kind of a positive feature of the theory that is kind of telling us about some new physics that are occurring. And they have a very nice kind of error correction interpretation of this picture in the context of the single-sided black holes that hopefully we'll hear about more tomorrow. So yeah, so I'm not entirely sure how to interpret that, but there's kind of even a third question that I think can be asked in light of these results, which is, what exactly does it mean to formulate a quantum extended Church-Turing thesis for quantum gravity? So our results kind of use this quantum extended Church-Turing thesis as a black box. We're just saying that if this thing is true, it should allow you to simulate what various observers experience in the wormhole. But we never got into the details of formalizing exactly what computation would look like in a quantum gravity theory. So I think it's a really interesting question to try to formulate this further. Like, how do you reason about computations that are being performed in different accelerating or non-accelerating frames? There's not like a global time here to be kind of considering when you consider computational complexity. And there are also questions about how does this AdS state encode the geometry of the bulk? Does it give you this global picture? Is it only reconstructing kind of causal patches, or what local observers experience in the theory? So I think that this is kind of, our results kind of pointing to a lot of interesting open questions that would be great to explore further. So with that, I think I'm out of time, and I'm happy to take any questions. Yeah, thanks for your patience.
A lot. Let's all unmute and thank Adam again. So are there any questions?
Actually, I had a small comment. I feel that the Q quantum ECT in the presence of gravity should merely say that gravity doesn't change anything. In other words, it should say that the existence of gravity doesn't enable you to compute anything you couldn't compute without gravity.
Yes, yeah, that would be another way of formalizing it. Sure, sure. That's to say somehow adding gravity to your theory shouldn't allow you to build a supercomputer that's more powerful than quantum computers.
Yes.
Exactly.
But I think if you formulated the quantum ECT that way, it wouldn't have led to some of your considerations.
Oh, why is that?
There wouldn't have been any tension between the quantum ECT and the fact that the wormhole volume is essentially unmeasurable in the CFT.
Oh, I see, because you're saying that if you took that viewpoint of the quantum ECT, then
Yes.
it wouldn't allow you to kind of simulate the experiences of observers offline with a quantum computer, or?
Well, it's not known. I feel that there are several things that are being combined here. So it's
Sure.
extremely unclear how we can simulate the experiences of an observer who falls behind the horizon of the black hole in the CFT. And that's quite independent of everything else in your lecture. So it's going to be very hard to conclude anything convincingly by an argument from that. Possibly we'll be able to conclude that we can't simulate that effectively, or that it's hard to simulate that.
Yeah. Sorry, go ahead.
No, you go ahead.
Oh, I was just going to say that I think that could be one way of actually interpreting our result, is that it's kind of formalizing in some sense why it should be difficult to simulate the experiences of observers in the bulk from the CFT. Like if there's an exponentially complex dictionary connecting them, that would be one particular way that you could have an obstruction to this.
Well, I would have liked that way of formalizing what you were doing, which I think you could have. Okay. To me, it would be more compelling to do that directly rather than going via discussion of the quantum ECT, because, well, to me, what's physically most natural is the quantum ECT. The ECT is formulated without reference to what are in detail the laws of nature. So there's no weak interaction ECT. So why should there be a gravitational ECT? I'd say that the most natural formulation is that the ECT is universal and doesn't care what the interactions are. And in particular, neither the existence of the weak interactions nor the existence of gravity should enable you to compute anything that you couldn't compute in a more simple model that had neither the weak interactions nor gravity.
Sure. Yeah. I think that's a reasonable way of formulating quantum ECT.
So. Okay, but then
I guess the form of quantum ECT I'm thinking about could be slightly stronger, though, in that I'm talking about, in the thought experiments we're performing, one's actually simulating different observers offline and then combining the results of those observers in some kind of non-physical way. So it kind of is like, actually, in some sense, wouldn't our kind of the way we're using quantum ECT kind of fall out of the way that you're suggesting formulating quantum ECT, in the sense that, if adding gravity to your quantum theory shouldn't really change its computational power, then that would indeed say that you should be able to simulate everything that happens with those observers with a quantum computer, right? Or am I missing something?
Well, the reason I'm hesitating is that it's unknown to what extent the experience of the infalling observer can be described in the CFT, and that makes me hesitate to try to answer your comments.
Sure. Well, I don't think that, you could also see a result as saying, well, if there were a simple way of using this dictionary to extract, say, the metric of the AdS space or something like that, classically, you can simulate what happens in GR, of course. You can program it into your computer or whatever. So if there were a simple way of taking your CFT state and extracting the global geometry of the bulk, which then, there you can just simulate even on a classical computer what happens to observers and estimate the wormhole volume, then that our argument would then say that that extraction procedure has to be exponentially complex. So there's not an easy way of just looking at your CFT state and reading out the geometry that it would be dual to.
Well, I think that's an interesting claim.
Yeah.
To my way of thinking, a route to that claim that didn't go through a discussion of the quantum ECT would have been more clear. But okay, it's just
sure. Fair enough. I see a comment from Scott Aronson in the chat. Couldn't we say the quantum ECT properly formulated can survive the challenge from this talk, but the talk shows an unexpected way in which one does need to be careful in formulating it. Oh yeah, that's interesting. So yeah, you could say that. I also, one thing I'd like to say is that I'd like to logically distinguish the quantum ECT from the statement the dictionary is exponentially complex, right? Like actually, it's maybe one way of interpreting Scott's comment is that the quantum ECT can survive so long as you think that this dictionary has exponential complexity, and that might be something that might seem strange to some people, or it might have been expected. Yeah.
Not make too much claims about what was or wasn't expected.
Sure, yeah.
Okay, showing that having a bound that it must be difficult to simulate the experience of the infalling observer is interesting, irrespective of our other discussion about the quantum ECT.
Yeah, thanks. Yeah.
Adam, could you just clarify exactly what you think it would mean for the quantum extended Church-Turing thesis to be violated in your sense, rather than the dictionary being exponentially complex?
Well, yeah, so it could be that there's
within the bulk, there's no violation, right? This is Edward's definition, is the Church-Turing thesis, where it's just, can I do a calculation in the bulk that would be super powerful? Then I just can't.
Well, yeah, I think the way that we were thinking about it is, maybe the dictionary we're talking about is the dictionary that maps the CFT state. So it's a map that takes as input the quantum state of the CFT and outputs, either a description of the bulk geometry or say the quantum state of the quantum gravitational theory, which is not entirely clear that's independently defined, but if such a theory were independently defined, then it could be that particular quantum state, right? So if it were the case that the dynamics of quantum gravity, if you throw gravity into the theory, somehow those dynamics become exponentially hard to simulate. So they aren't described by a local Hamiltonian. We know that those are easy to simulate. But if they had some super crazy dynamics as to what one would experience to one's quantum state if one jumped into a wormhole, then one wouldn't be able to kind of efficiently perform our thought experiment of simulating the observer's experiences within the wormhole. So I would say that our argument is saying either the dictionary or the dynamics of the quantum gravity theory would have to be exponentially difficult.
But can't I just do the dynamics on the CFT side, where we know the CFT doesn't violate quantum Church-Turing, right? That's sufficiently simple.
Sure. That's
so then we do that, and then if the dictionary is simple, then it seems like, right? Doesn't that just prove the dictionary directly has to be complex? Because if the dictionary was simple, I can just evolve on the CFT side and then use this simple dictionary to work out what's going on in the bulk, and then I'm done.
I see. Yeah, that's an interesting point. Yeah, I guess if you're assuming that, after you, okay, so I guess you're saying you run the dictionary in the opposite direction, would this work? Yeah, potentially.
Yeah.
So then, I should emphasize that in our whole arguments, we were only really considering the dictionary from the CFT to the bulk. But if you think about running it the opposite way, then there could be another possibility that the CFT dynamics are not efficiently simulable.
That seems very
yeah, I agree. That sounds more speculative.
So how exactly do you calculate or estimate the complexity of a duality? If I take something easier than AdS CFT, it's something that doesn't involve quantum gravity, just a duality within quantum field theory, S duality and n equals 4 or something like that. How do you estimate the complexity of that duality or the complexity of the dictionary?
Well, I don't think that it's something that would be easy to read off or something like that, right? I think the complexity of something is different from having a formula to compute it, right? Yeah, I don't think in general that there's a way of estimating the complexity of generic dualities. I think it's more just saying that this duality looks like it's giving you a free lunch somewhere because it's it's equating something that's really hard to compute with something easy to compute. Something looks off there, right? So, but if there are dualities between if they're efficiently computable dualities between theories in which kind of everything's exactly solvable on both sides or things like this, then maybe, yeah, there need not be contradictions for generic dualities. I think this is something that's just this could be something that's just very particular to AdS CFT. Does that answer your question, or were you trying to ask something?
Yeah, partly. I mean, some dualities, you know, for example, just within QFT relate strong coupling to weak coupling, right? So weak coupling, we have many methods to use to try to calculate stuff, and strong coupling, we don't know too much what to do, right? So if,
sure.
So if you didn't know anything about the duality, you would say, well, it seems super hard to compute anything at strong coupling. But now the duality may say, actually, not that much, because you have this trick. I'm just trying to understand.
Well, you can see dualities as like an algorithm, right, to allow you to perform a computation
right.
that's hard than the other. I guess if you have such a duality, I would say it tends to be arguing that the problem you thought was hard is not in fact hard, because there's actually this non-trivial algorithm using the duality to compute it. I think what's unique in our argument is that we have some formal evidence that the problem you thought was hard is actually hard. Because, you know, it requires breaking some pseudo-randomness construction. So.
I see. So you have a sort of more first principles way to say this is hard.
We have a more first principles way of saying, well, yeah, this is actually genuinely.
This is actually really hard.
Problem. This duality is mapping it to something easy. Then we can conclude that the duality has to be actually complex.
So I had a comment that's related to this quantum ECT. I was just wondering, you said something at the beginning about collating the experiences of different observers who fell into the hole.
Yes.
And that you may be doing this in your algorithm, your simulation, but it might not actually be physically possible for them to get together in the black hole and put things. So I wonder if that might help alleviate the conflict with the extended quantum ECT. The fact that actual observers in theory could not get the answer.
Yeah, I guess for us, I view this argument about collecting different observers' experiences more as a thought experiment, as a way to argue that there should be an efficient algorithm to extract the information from what's happening to these observers. So I don't think there's any need to instantiate the argument kind of in the theory. Does that make any sense? Maybe this is a philosophical point, but.
Well, no, it does make a lot of sense. I just think that one might want to formulate an extended Turing thesis as something about what agents can actually calculate using the physical means they have available.
Oh, I see. Yeah. As I said, yeah, I see what you mean. So that could be one way of suggesting like a very, this is a little more like narrow of a quantum extended Turing thesis or something.
Yeah, perhaps.
But I guess our argument is saying, though, just to kind of, I'm trying to think through if this would give one something different. You know, if you only believe you can simulate what happens to individual observers, you know, certainly in quantum algorithms, one could, you know, simulate each universe separately and then combine them, right? So in terms of formulating, like, I guess I'm not entirely sure why something like that would be disallowed and kind of defining a form of computation in quantum gravity if one's really thinking about, you know, these are all states on qubits and you're applying poly-size quantum circuits to them, right? So, but yeah, you could think about some ways in which you could formulate it and you somehow explicitly disallow those sorts of computations.
Well, I mean, I think I was saying if you know, reasonable interpretation of a physical entity could, you know, an IGUS, that, according to Murray Gell-Mann, could actually get the answer, then I would say, yeah, that's a computation. But sort of the spirit of extended Turing is, you know, let's think about the physical means that we actually have available to do stuff, and maybe they're more than we had modeled with classical computation. But you know, but yeah, it would still be an extremely interesting thing if, you know, that were hard for agents to get, but it was somehow not hard from this more external.
Not hard, yeah, from this more external kind of computational bird's eye perspective of the space. Yeah. Yeah. No, I think there are a lot of subtleties. I think, yeah, you're just getting it there. I think there are a lot of subtleties to unpack here if you're trying to formalize this. So.
Yeah, thanks.
Yeah, thanks.
Okay, so we've had a few questions. I should probably close the sort of official part, but don't go anywhere yet. We'll still have time for off the record questions for both Jeff and Adam. Before I do that, I just want to remind everybody that tomorrow there's the 2 usual sessions, which are, I guess, for Europe, morning and evening. But on top of that, there's one extra talk by Benny Yoshida at 4 p.m. European time, 10 a.m. Eastern time.